So, bond dissociation energy is the amount of energy that must be supplied to break bonds and to separate atoms in an isolated gaseous molecule. So, scientists have determined the amount of energy that is required to break bonds in different compounds, and they've done this in the gaseous state. So we're going to take a look now and identify chemical reactions as either endothermic or exothermic, and explain how the heats of reaction relate to the law of conservation of energy. Before we move on with the rest of the content, I'd like you to take a moment and try to answer this question. Now, you won't see it again during this video, but we will review the answer once we meet for our practice session. So pause the video, take a look at the problem, and choose an answer. You will definitely have an opportunity to change your answer once we meet in class, but it's a thinking question, and we will definitely come back to it later when we meet. All right, so the strength of a covalent bond is measured by bond dissociation energy. If we have a really strong bond, it is stable, and you must supply a large amount of energy to break that bond. Let's think about it. Do you think that, remember what a bond is now, right? If we're talking about covalent compounds, a bond is what? It's a pair of shared electrons, right? So, and if we're talking about ionic compounds, it's when an atom donates an electron to another atom, right? And then they stick together close because they have a positive and a negative charge, and they stick together. Now, if we drop an ionic compound in water, it will dissolve, meaning that those ions separate from each other, right? And so ionic compounds, they're a little different from covalent compounds when we're talking about bond dissociation energy, because we can overcome that energy with ionic compounds just by dropping them in water if they are soluble. So we're mainly talking about the strength of covalent bonds, right? And if we consider that a covalent bond is a pair shared electrons, do you think that you would require more energy to break a single, a double, or a triple bond? Which one of those do you think you'd have to add more energy? A single, a double, or triple bond? A triple bond. Why? Because we have more ions that are interacting with, not more ions, pardon me, more electrons that are interacting with each other. And so it's going to take more energy to break a triple bond than it would be to break a single bond, and even to break a double bond. So double bonds between the same types of atoms, between, let's say, a double bond between a carbon and a carbon is going to have more bond dissociation energy required to break it than a single bond. And then a triple bond between two carbon atoms, you would have to add more energy than you would for a double bond. Okay, so the stability of a bond increases as the bond energy increases. So the higher the bond energy, the higher the stability of that bond. And the more stable a molecule is, the less reactive it is. We already mentioned that a minute ago. Remember, we said stability has to do with reactivity. So if I have a high total bond energy for the entire molecule, it's going to be more stable, and it has less potential energy to react. The opposite is true for low bond energy. So the lower the bond energy, the less amount of energy that we have to add into breaking bonds, the less stable it's going to be. So if I only have to put a little bit of energy to break these bonds, then it's really not a stable, the bonds aren't that stable, and we can say that we have more potential energy to react. So low bond energy, high potential energy. High bond energy, low potential energy. All right, they're opposite. Okay, it's an indirect relationship. So let's say high BDE, low potential energy. Low BDE is high potential energy. Okay. Now remember, energy is the ability to work, to do work, right? So the potential energy that's stored in these bonds can do work. So let's take a look at some bonds. Notice here, let's go to the carbon. Notice here that a carbon-carbon double bond requires only 147 kilocalories per mole to break that bond, whereas the carbon-carbon triple bond requires 201 kilocalories per mole um, to break that bond. Take a look also at the nitrogen-nitrogen bond. A single bond is only 38 kilocalories per mole, whereas a triple bond over here is 226 kilocalories per mole. So notice that the more electrons that are shared between a set of atoms, the more energy that is required to break those bonds. Okay. So what are the energy units for chemical reactions? Well, we know that a chemical reaction involves the loss, um, involves an overall chemical reaction is going to involve the loss or gain of energy. Actually, every chemical reaction includes a loss and a gain. So energy is lost and gained for every single chemical reaction. And why is that? Because we have to put energy into the system to break apart the reactant atoms, right? And then energy is given out of the system when we reform those bonds. Remember a few slides ago, we said that bonds, you have to put energy in to break a bond, whereas you're going to release energy when we're forming bonds. So the SI unit is the joule, and you'll often see kilojoules used because there's generally a large amount of energy that is transferred or energy that is produced or lost overall for chemical reactions. So we generally use kilojoules instead of joules, but you will have problems in which you'll see both kilojoules and joules. So a chemical reaction in which the overall difference between breaking and making bonds is that we absorb more heat than what is let out. We have an endothermic reaction, right? So here that means that breaking bonds energy is greater than forming bonds, right? And that's endothermic. And for this, we'll say that energy has a positive value and energy is gained. Whereas a chemical and physical process that releases heat is going to be exothermic. And what do we mean by that? We mean that the forming bonds for a chemical reaction is going to be greater than the breaking of those bonds. So if we're talking about freezing water, we have to release heat. So here, note that a chemical or a physical change can be considered endothermic or exothermic, all right? So if I have a reaction that's A to B, um, and it's a positive amount of energy that's added and required in the reaction. Well, if I reverse that reaction and turn it around and go from B to A, then that means that that process has a negative amount of energy that's associated with it. So that just means if I have to put energy into a reaction going forward, that means that I have to take energy out going in reverse. So the law of conservation of energy says that energy can neither be created nor destroyed. in any physical or chemical change. So how do we determine what is lost or gained in a chemical change? So remember, there's energy that goes into breaking bonds, and then there's energy that is released when forming bonds. And so there's a total amount of energy that is associated with this chemical reaction, and we call that the heat of reaction. And it's the difference between the heat that's absorbed in breaking the bonds and the heat that is released in forming new bonds, right? So the conservation of mass says that I can't have any other atoms or any other, I have to start with the same mass and end up with the same mass. Conservation of energy says that I have to have equal amount of energy on both sides of this reaction. Either I'm putting the energy in or I'm taking the energy out. And how do we measure? We measure whether heat energy is lost or gained by looking at the temperature. Okay, so if you have a reaction, you've got a temperature sticking, you have a thermometer sticking in your beaker while the reaction is going on. If the temperature goes up in that solution, then we know that heat energy is being given off. And so that we consider an exothermic reaction. Now, that is because those molecules are rearranging, those atoms are rearranging, and in that rearranging, energy is given off to the surroundings. So, what are the surroundings? If we go back to that double displacement reaction, it's going to be the ions that are still floating around in solution. It's going to be the solvent. It's going to be the beaker. It's going to be the air, right? If the reaction now is endothermic, then the temperature is going to go down. Why? It's because that chemical reaction that is occurring where those ions are coming together now and making that precipitate. Remember, I'm only using this as an example. It goes for all chemical reactions. But the energy is being absorbed from the surroundings. What are the surroundings? Those ions that are floating around in solution, the solvent, the beaker, the air, okay? And that's why the temperature goes down, all right? So we call the heat of a reaction enthalpy change, and it's delta H. And that is the amount, the overall amount of heat energy that is absorbed or released during a reaction that takes place at constant pressure. So, when does the change in energy occur? When our reactant atoms interact with each other. So that means that they've got to bump into each other in order for the chemical reaction to occur. Like a chemical reaction can occur if molecules don't actually touch each other. So the more they bump around each other, the more they're going to interact with each other, and there's energy that's involved in that process. There's energy changes when the bonds break apart. So if they bump into each other hard enough, they bump into each other hard enough, and then those bonds between the atoms are going to break apart. And now there's also another energy change when we are forming new bonds. So let's say the atoms in our reactants, the molecules in our reactants, they bump into each other. Now we have these atoms that are going to rearrange themselves by joining to other atoms in the system. Okay, and we use delta H as the enthalpy change system, and it's the difference between the enthalpy of the products and the enthalpy of the reactants. So delta H is going to be the enthalpy of the products minus the enthalpy of the reactants. Now, what is this enthalpy again? It's potential energy. Okay? Potential energy. There's something called, well, I'll review that in a minute. So it's the potential energy in our reactants and our products. So delta H is considered our, well, the change in potential energy between our products and our reactants. Okay, and delta, remember from delta T, means change in. Okay. All right. So now we're going to take a look at how to determine enthalpy of reactions from graphical data and use the relationships in a chemical equation to help us calculate the amount of heat consumed or produced in a chemical reaction. So let's review. For exothermic reactions, if the energy required to break the bonds is less than the energy released, then there's a net energy release, and we call that exothermic, right? So we have to break the bonds between our reactant particles, and we form new bonds to make our products. The reverse, well, okay, so let's take a look now at the graphical representation, and let's take a look at a chemical reaction to help us determine how would we know that we're looking at an endothermic or exothermic reaction. So for the exothermic reaction, remember heat is released. And what does that mean? We're looking at potential energy here, right? That means that the potential energy of our reactants is really high, not really high, but higher than the potential energy of our products. So in this reaction that we're looking at here, the hydrochloric acid is more or less stable. More stable because it has a lower potential energy. Okay, now if we're taking a look at a chemical reaction and we see that energy is added as a product, this is just saying that it is released in the reaction. So we have our reactants and then we have our products. So energy is considered a product, and that means that it's being released. Now, if we were to just see delta H written by itself, because this is an exothermic reaction, we're going to say that it has a negative value. Why is there a plus sign here? Because it is yielded in the reaction. It is considered a product in the chemical reaction. Okay, so here we see the heat energy written as a part of the balanced equation. If we see it by itself, it's always going to be written as a negative value. So exothermic reaction now an endothermic reaction means that the energy required to break our bonds, energy required to break bonds are larger than the energy required when those bonds are formed. So remember, we have to add energy into breaking these bonds, and then we release energy when new bonds are formed. So what that means is we will need an external supply of energy for this reaction to occur overall. Okay? So what does this look like? Well, in an endothermic reaction, we know that heat energy is absorbed. So notice that our products, our products have more potential energy than our reactants. And in order to get from our reactants to our products, energy must be absorbed. Now let's think about nitrogen and oxygen. Where do we know that nitrogen and oxygen is in our daily life? It's in the air, right? Do the molecules in air, the nitrogen and the oxygen, do they go around reacting with things? Just no, they remain nitrogen and oxygen. They're relatively stable compounds and they don't want to react. And the only way that we can get these two to react is if we add energy into the system. So if we're looking now at a balanced chemical equation, notice that because energy must be added into the system, it is written on the left-hand side of our reaction because it is now a reactant. For an exothermic reaction, the energy is a product and we write it on the right-hand side. But being that this is an exothermic reaction, energy is added on the left-hand side of the reaction because it is a reactant. Now, if we were to see delta H by itself, it's going to have a positive value. Why is it positive? Because it's telling us that the energy is being absorbed and not released. So, if we're looking at something like combustion, this is methane. This is the reaction that occurs on your stove, where once you turn the stove and it goes tick, 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 that is a spark of energy that is added so that this reaction can occur. And why do we use methane to cook? Because it gives off a large amount of energy per mole. And so we can use that energy. What does it do? It goes into the atmosphere, it goes into the surroundings, and we can use that heat to boil our water, to cook our food. Okay? Whereas here we have a decomposition reaction in which we know that all decomposition reactions require an input of energy. Why? Because we are breaking bonds. We are mainly breaking bonds. Yes, we're making new bonds, but we have to put a lot of energy in those bonds. So what do we see here? We see that our reactants have low potential energy. We have to add energy into the system in order to get to our products. So what does this mean about endothermic reactions? It means that the products in endothermic reactions are less stable and they would rather go in reverse and be reactants. They'd rather not go in this forward direction. Okay? So if I look at the combustion reaction, notice that our reactants have high potential energy, but our products have low potential energy. Notice water is not reactive, and neither is carbon dioxide, right? So those have less potential to react. And the difference between our potential energy between our products and reactants is going to be our delta H.